So we will continue our discussion of the idea of how to combine an alternating component of stress with a mean a component of the stress and predict the fatigue lifetime or the factor of safety. The last thing we've discussed is that you have to consider also the fatigue stress concentration factor, and this fatigue stress concentration factor would be applied to your design. So we will move on from here and look at the possibility of having um, the alternating and the mean stress as ways of how to combine them to predict failure. So the idea is that if we just take the ratio of the alternating divided by, suppose we take the endurance limit, this is a fraction that tells us how far we are from the material failing by the if the alternating stress is close to the endurance limit. So let's call this D1. And then if we have a mean component of the stress, sigma mean, and we ratio this to the yield strength of the material, then we would consider this as a fraction indicating how close we are to yielding. Now, if we have both alternating and a mean stress, then we can combine these linearly or non-linearly, depends on the data. But if we suppose we combine them linearly, for example, D1 plus D2, that should give us an indication that we should not exceed 100% under any conditions. So that's basically the idea of how to combine the alternating and the mean stress in some fashion. So there's a variety of ways to do this combination, and the variety of ways are actually dependent on how we would interpret the experimental data. So what I'll discuss here is different methods to combine both the alternating and the mean stress and then use that in a particular design. So let's first look at the first method in this approach. And the first method is that we'll discuss is called the modified Goodman method. And in modified Goodman method, we would combine both of them in such a way that we would have sigma alternating divided by S endurance, for example, plus sigma mean divided by S ultimate. Strength of the material should be equal to 1. This will be our criterion for adding the damages. However, if we consider that the sigma mean is ratio to the ultimate, then there's a potential possibility that the total stress, which is sigma alternating plus sigma mean, the sum of these two, can exceed the yield point. If it exceeds the yield point, then this can raise some questions. And therefore, the modified Goodman has to consider a possibility that it should not exceed, the sum of these two should not exceed the yield point. So the idea here is that we want to, first I'm going to show you a diagram, and this diagram illustrates how you combine the alternating with the mean and not exceed the yield, the strength of the material under any conditions. And then we will talk about, instead of using a diagram, we will use equations, which would be much easier to use because we can always either program them or use them on our calculator. So here in this diagram, you see that I have, we're going to plot the mean stress on the abscissa, and we will plot all other components of the stress on the ordinate. So if we, for example, want to plot the mean stress versus the mean stress, it will be a 45-degree line, which is right here. So this is the mean stress, as a function of the mean stress. So that's very easy to understand. And now if we add to that mean stress an alternating stress, so we add a plus alternating and a minus alternating, then we will produce two lines. One line that is the maximum, because the maximum is the mean plus the alternating, and the other line is not parallel to it, is the minimum, because this is the mean minus the alternating. Now these will go up to when the mean is 0, that's for fully reversed, and you can see here for fully reversed, the maximum is equal to the minimum but with a negative sign. When we go to the compressive stress range, these two should remain parallel because we are finding from the data that the mean stress doesn't have any effect on fatigue strength if it is compressive. So there's no problem. We can just kind of ignore it, and therefore this will remain parallel in the compressive range. In the tensile range, the key point is that this maximum stress, at some point, if it is large enough, it can actually cross the yield strength of the material. You can see the yield strength is right here. So the maximum, if it is very large, it can cross that yield strength on the first cycle, essentially, because in modified Goodman, the sum is allowed to go all the way to the ultimate if needed. And therefore, we have to set a limit on the maximum, and that limit is this constant straight line here. So that's the maximum possible for the maximum stress to be not to exceed the yield. Once we set that limit, then we can determine the intersection point here, which is S yield on the mean stress axis, and it's also S yield on the maximum. And then we would be able to also find the coordinates of this point, which is less than S yield. This can be computed, and then it is equal to S yield on the vertical axis. So this shape here is where we have the design space. So the mid-range stress will be here. The maximum will be determined by the top line. And then in this region here, we have to be careful and not to design outside the yield stress. So this is a graphical way to represent the design on the modified Goodman diagram. Another method for design is also graphical, and the graphical method is called the master fatigue diagram. And in this method, just similar to the modified Goodman, we want to plot the mean stress and the alternating stress, and we want to plot the minimum stress and the maximum stress, and then we want to show how they are related and use it in design. So in this case, what you'll see here is that I have I essentially plot I have on this horizontal axis, I plot now the minimum stress, and then on the vertical axis, I plot the maximum stress. So I have the maximum stress here and the minimum stress here. And then if you will see here, let me just move this outside. So if you see right here, I can plot the mid-range stress, which is a 45-degree line, because the mid-range stress, which is the mean, is the sum of the maximum and minimum divided by 2. And on this, I can also have another 45-degree line, and the negative minus 45 degrees or 135 degree. This is the alternating stress, because this is the difference between the maximum and minimum divided by 2. So now I have a space, which are these two axes, the mean and the alternating, very similar to the modified Goodman. So if you look at here, the modified Goodman, I used to have the mean here, sigma m, and also now the alternating. So now if you look at the master curve for fatigue design, this is your sigma mean, and this is the sigma alternating. And so you're looking at it with a rotation of 45 degrees. Okay, so if we have the two of them together, then the experimental data can be plotted such that we have to design inside this curve, and this is for 10 to the 6 cycles inside that curve for 10 to the 5 and then 10 to the 4 and so on. So this can be a result of a lot of experimental data where the combination for any design point like A here has to be, we have to have a mean value and you have to have an alternating value, and it should be below the experimental data so that you have a safe design. So these are kind of some of the methods that have been used in the past, and these methods have been successful for past designs, but we can get the same information if we use algebraic equations. And that's what we will do next, is that we would like to find algebraic equations to combine the damage fraction due to the mean stress to the damage fraction due to the alternating, and then add them up together in some kind of fashion here. And what we will do is before we move on to this, we want to continue our discussion of what's happening when you have an alternating component versus the mean component. So sigma mean is here, sigma alternating is here. All right, so if I just want to find the relationship that is called the modified Goodman relationship, which is sigma alternated divided by SE plus sigma mean divided by S ultimate equals to 1. This is the equation of a straight line if you have the sigma mean on this axis and sigma alternating on the vertical axis. That will give us a straight line equation, and the straight line is going to be represented here, where the intersection with the horizontal is at the ultimate stress, and the intersection with the vertical is at the yield at the endurance limit. So this line is sigma alternating over SE plus sigma mean over SUT is equal to 1. Now the problem that we discussed before in the modified Goodman is that there is kind of a range here that's kind of dangerous, and this range is when we wanted to guard against the maximum stress not to exceed the yield. That's why we had to cut it off right here. So we don't want to go here. We don't want to go to the yield. And instead of using the modified Goodman construction, which is, takes some work to do this construction, then an easier way is to use the so-called Langer line. And the Langer line is a line that has a connection between the yield point of the material on the horizontal and the vertical. And it tells us that under any condition, under any circumstances, whenever we have the mean and the alternating, the sum should not be exceeding the yield point. In other words, the Langer line is a line where we are, if we add up the damage due to the alternating to the damage due to the mean, the sum of these two damages should not exceed the yield point, and it should be expressed in this form. So we would express it as sigma alternating over S yield plus sigma mean over S yield must not be equal to greater than 1. So this is a check that both the alternating and the mean, if you add them together, the sum is going to be the maximum, and it should not exceed the yield point. So we have to, under all conditions, we have to be below the Langer line here when we combine the alternating and the mean. So if you look here, you see that there is a region of danger right here because it's possible that we exceed I'm sorry. So let's backtrack here. So there's a region of danger that we exceed the yield point right here because in this region it's possible that the sum of the mean and the alternating, or the sum of the mean and alternating, will be such that the sigma max can exceed the SCO. So it is possible in this region here. So what we need to do is find the intersection point here and then make sure that our design does not go into this region where the maximum exceeds the yield point. So this region is very similar or pretty much the same as the modified Goodman, but if you look at it here, it would be the modified Goodman is, if we don't apply any limit, then we would get into this regime here, but applying the limit, we are kind of limited to the regime. So let's just continue here and have our discussion in the way that we are able to determine now the combination of the mean stress and the alternating stress and how they can be added. So I'm going to see if we can move on to the next section, and in the next section we will be able to do some examples.